Hi everybody, welcome to another section in Calculus 3, Limits and Continuity. First, just review real quick what did we define the limit of a function of one variable. This is the beginning of Calculus 1. So I just copy and paste that definition here. So we define using epsilon and delta. So meaning that if we talk about the limit of the function at 8 is equal to L. So if we choose the values that is close enough, if it is close enough to A, then the value will be close enough to L. So that's essentially what the limit is. Of course, the definition precisely is this. But what I focus on is the limit, the way we define that as a function of one variable. Then when we go to two variables, what will be the difference? What will be the difference? So we have coordinate axis and say the function or like that, and we look for the limit at this point A. Right. So when we're trying to find the limit of the function, we'll find the y values that the function approaching to from the left and from the right. If they come from both sides, go to the same point, that will be the limit of the function. Whether the function is defined at the point or not, it might be an empty circle here, it doesn't matter. What the function approaching to will be the limit, and we take the limit of the function when it goes from both sides. That is important. Remember, this is the definition for one variable. So if it is one variable, meaning that it is one dimension. If it is one dimension, so from here we can only go from the left. We can go approaching the point from the left and approaching the point from the right, as there's no other option, right? Now, if we go to two dimension, that will be a lot more interesting and open a lot of more possibility. So let's look at the definition real quick. Still, definition using epsilon and delta. So the function f has the limit L, the function limit L as the point xy approaching A and B, right? So the point is in two dimensions, so they have two components, x and y. So this point approaching that point, written like this: when x, y go to A and B, meaning x to A and y to B, or p to p naught, either way. We say the limit of the function equal to L if any epsilon greater than 0, and usually when we define that epsilon is extremely small, there exists a delta positive such that f of x minus L less than epsilon whenever xy is in the domain of that, and the difference between xy and AB is less than delta, meaning that we can get arbitrarily close to L if we choose the point close enough to A and B. Right? Let me say that again. This means any epsilon positive, meaning that the function and L, they get extremely close as we want to. So we say f of x, y is close to L as we want to if we choose the point xy close enough to AB. Right, so that's essentially the definition of the limit. And the way we define here, we use absolute values, but here we have to use the magnitude because there's more than one variable. Right, now the interesting part that I said before. So we have the point xy in general, could be anywhere, and we're approaching to the point A and B. Right. So the way we're approaching this is we can go straight here. This is one way to do it. Or we can approach in the spiral, as long as, right, the distance from that point to here get closer and closer, right? So from xy to AB there's is infinitely number of paths, and that's why this is a lot more interesting thing about in function of two variable. We go from one point to another. It's not like this from the left or from the right. In two dimension, from one point to another, there's infinitely path from one point to another, and so we cannot define based on any path in particular. We just define based on the magnitudes of those points getting closer and closer. Right. So keep that in mind. There will be a bunch of different paths if we have more than one variable. Right. So properties of limit. Limit of constant, of course, there's nothing to substitute in. If there is something to substitute in, we substitute in the point. So there's nothing new here. The rest, these are the properties of the limit of one variable, two variable, doesn't matter. Those should not be a problem. Limit of a sum is the sum of the limit. Limit of a difference is the difference of the limit. Constant multipliers, take it outside. So limit, integral, derivative, summation, all of that have these properties. I mean, except for the summation. Should have these properties, I should say. The product, the quotient, and power, those reserved for the limits. But still, like I said, there should not be any problem with these properties. Right. Now, first rule when we're trying to find limit, of course, is put in the numbers, see what happens. So this is the easiest. For example, I'm just going to put in the numbers and see if it is equal to. So I'm not going to write equal to right away. I'm just say x equal to 2. So I'm going to put 2 in for x. And y go to 8. X go to 2. Y go to 8. So that's what we have. Now, that will be 3 times 4 times 8. Yeah, just it's 96. And this is 2 times 8, 16. Square root of 16 is 4. That gives us 100. Now this is a nice number, so we make the limit equal to. Right? Right, so that's what the limit is, the easy case. Like I said, it will not be easy when there's different path. That we have to consider. But if it is defined, yeah, that's the limit. No problem. Yeah. Just like the limit of one variable function. Right. If we have indeterminate or something like that, that is the big problem. Worry about that in a minute. Right. Open and close set. At this level, we just briefly go through this. When we actually, if you are a math major, you spend probably 3-4 different courses study about this intensively. Right. So we define an interior point, an open set, and then a boundary, and then a closed set. Right. So let's go to the, like I said, we'll go over this briefly. An interior point lies entirely within R. That what's the big deal? Which means it is possible to find a disk centered P containing only point of R. So we have interior point, and that lies entirely within the region. Is that what is the big deal? That's what we call the interior point, right? Right. Actually, it's mathematically, this is really precise. Let's say we talk about an open, say about this region, for example. And of course, obviously, we have here is an interior point, right? So the definition says if we have an open disk, a disk that is completely inside of R. So if we draw the disk that is small enough, if we draw the big disk like this, there will be some point outside of the region R. This is the region R. If we choose the small disk, then that disk is completely within R. So that point is called the interior point. And they said, what happens if we have the point that is extremely close? the point here is it doesn't matter. If it's closed, we're going to use the disk of a smaller radius, but we still have the radius, have the disk around the point, and this is completely inside the region. By that definition, that is called an interior point. Right. Next, a boundary point. Boundary point is the point here. It says, so the language here is actually very precise. When we say interior point, we said, which means it is possible to find. Whereas here we say the boundary point is every disk. So in here, doesn't matter what radius that we choose, how big or small of the disk, there will be a point inside and this is a point outside. We can make a big disk, there will be a point inside or point outside, or a very small disk. Doesn't matter how big or small the disk, there will be a point on the outside, there's a point from the inside. So that's why I will call those points boundary points. All right. Next, an open set and a closed set. An open set is anything that consists entirely of interior points, and the closed set is the boundaries and the interior point. So I'll give you an example here. Or we can think about this as one dimension. So for example, we talk about an open interval here, because by the name we say it's open, meaning it doesn't matter how close it is, we can always find the interval around the point that is completely inside of it, right? Yeah, if the point might be here, then we choose that interval, open interval, completely inside the 1 and 3. So that's how we define an open set. Like I said, at this level, that's all we worry about. If you go to math, that you study this intensively in various courses. Right, now focus here is on the limit. Right, just find the limit. The first rule finding limit is put in the numbers and see what happened. 4 and 4, 4 square minus 4 square. That gives us 0 over 0. Well, indeterminate and two variables cannot use the Hospital rule because we don't have derivative yet. Remember, it's just like in calculus 1, we have to define the limit before we define derivative. So we don't have derivative. Here we just study limits. So there's no L'Hopital rule here. So what can we do though? Let me write the problem again. Right. What can we do? Because we have both 0 from the top, on the top and the bottom, which means they share a common factor. And the factor that we have is a difference of 2 square. So we have limit. So x squared minus y squared is x minus y, x plus y. And we can cancel those. And we have a limit x goes to y, xy goes to 4 and 4 of x plus y. Then we put in 4 and 4. 4 plus 4 is 8. And that's what the limit is. Right. So look at the graph real quick. Right. I just type graph. I can make this window a little bit bigger. Right. That better. Graph I just have the function x squared minus y squared divided by x minus y in Google search, and we have the graph. Yeah. Right. So this is just a plane, and if we choose x to be 4 and 4, yeah, we can actually find the values. So it's just a plane, so the limit should be simple. Right, I said the graph here does not help us as much, but we can find the limit that way. Right, now let's look at something more interesting. Alright, so find the limit as x, y go to 0, 0. So I put 0, 0 in for x and y, and we have 0 over 0. Once again indeterminate, but no L'Hopital rule. So we have to do something clever. Right, first, this one I'm actually will look at the graph first. So we're going to graph, just type graph x plus y square divided by x square plus y square. Right, now you see, let me go back here, right little, okay, like this. So we have the x-axis, this, the y-axis, this, and the z-axis, the vertical axis. As you see, if we look on the top here, if we go along that line, the limit is different. But if we go along this line, the limit is different. Let me rotate, you see. You see, if I go in this direction, the limit is different. But if I go along this direction, the limit is different. And what is this direction? As you see, this one is in the middle of the x and the y axis, meaning y equal to x. Right. So when we see this, the limit does not exist. Oh, sorry, wrong one. Right. So take a look. We have the function. Now remember, we go to 0, 0, right? If we go to 0, 0, we can say let x equal to 0, and then we let y go to 0. Right. So this is a lot of different way to approach this problem. So here said, consider if we go along the x-axis, if we go along the x-axis, meaning that y equal to 0, and then we let x go to 0. So in that case, we're approaching along the x-axis with this. So I'm going to write the limit again. So we have that. Now, since we go along the x-axis, y is equal to 0 and x go to 0, so we just have limit x goes to 0 as we set y equal to 0. Right? Y, so we have x plus 0 square, x square plus 0 square. So y is equal to 0. We're going to just let x go to 0. That is where we go along the x-axis. Now, on the top we have x squared, the bottom we have x squared. Of course, that cancels out, we have 1. So, if we look at this along the x-axis, which is the one in red, the limit is equal to 1. Here's 1. Yeah, that's it. Right. Of course, if we can do the same thing for the y-axis, we're going to get the same thing. Now let's try something a little different. How about, because we can go to the point like this, or we can approaching the point 0, 0 in this direction, where we say y equal to x. So if we do this along the y equal to x line, in this case x is equal to y, and then we let x equal to 0. If x go to 0 and x equal to y, then y go to 0 as well. And we let x equal to y, right? And then we just have x go to 0. Right? This might not help at all, but on the top we have 2x squared, 2x and then square. The bottom we have x squared plus x squared is 2x squared. Right, actually it does help definitely. So we have 4x squared on the top, 2x squared at the bottom, x squared cancel out, we have 2. So along y equal to x. Right, let's do this. Let's z go from -1 to 2. Right. So when y equal to x, which is right in the middle of the xy axis, we have 2, which is good, right? That is 2. So the values go to 2, which is here. Yeah, 2 is there. Right, and this is equal to 1 when we go along the x-axis. So how do we look at this along the x-axis? So like this, parallel to the x-axis, it is equal to 1. Right, now what we see is if we go along this path, we have 1. We go along the other path, we have 2. So if they don't go to the same point, limit does not exist. Of course, we can choose y equal to -x, or the x-axis, the y-axis. Those are the common path. So that means if we can find if the function approach 2 different values, when it approaching to the point, then the limit does not exist. That's exactly what we have here. So we just choose a different path. If the limit are different on different path, then the limit does not exist. Simple as that. Right. Continuity. Continuous. A function is continuous. At just line count 1, 3 things need to happen. The limit exists, the function is defined, and they are equal. So exactly what we have here. So limit exists, function is defined, and they are equal. Then the function is continuous at that point. Right. This one is a lot more interesting. Let's look at the graph and see what happened. I'm going to graph this function. Right, let's check the whole page here. Oops. Right, I'm going to graph 3x squared, 3xy squared, sorry, divided by x squared plus y to the 4th. Oh, come on. Why we cannot graph this? Oh. Yeah, I have tried something else. Alright. That better. Sorry, I have to switch to something else. This is called the cow plot 3D. Alright. That's what we have. So Google doesn't work for that sample. Right. How about now? That look interesting. But once again, now let's focus on this. Okay, stop moving. Okay. It look like there's a parabola here, right? And you see the limit 0, 0 look like it approaching different values. So the limit doesn't seem to exist here because it look like at 0, 0 it's approaching different there and different here. Right. Once again, that is cow plot 3D. Right. So it look like there's along the parabola path and along different path there will be different values. So what is this path? Right, so that is right on the y-axis. Right. So let's just determine the point which the function is continuous. So this function, if it's not equal to 0, 0, that obviously continuous. Which is interesting to find what happened at 0, 0. So at 0, 0, is it continuous? So once again, continuous limit exists, the function is defined, certainly the function is defined, and they're equal. So we just need to find the limit, because if the limit exists and equal to 0, then it is continuous. Otherwise, it's not. So let's take a look at different path. Let's choose along the x-axis, y-axis, doesn't matter. If we go along the y-axis, meaning that we're going to let x equal to 0, and we let y goes to 0. Right? Everything on the y-axis, x equal to 0. So we just need y go to 0 when xy go to 0, 0. So we take the limit as xy go to 0, 0. Notice that it go to 0, 0. So if it go to 1 and 2, right? If we talk about the limit that go to 1 and 2, do not use the along the y-axis, because the y-axis does not go to 1 and 2. So actually the y-axis actually go through the point 0, 0. So we have to choose the line or the path that go through the point. That is important. Now we did say that x equal to 0 and y approaching to 0. So we just say the limit y go to 0, because x already is 0. Y square, we still don't have that. 0 square plus y to the 4th. 0 times anything is 0. So we just have 0 over y to the 4th. 0 divided by anything is 0. So this is equal to 0. So along the y-axis we have 0. If we do that along the x-axis, we should have 0 as well. How about along y equal to x? Along y equal to x, meaning that we're going to let x equal to y. And we're going to let x go to 0. Then y will go to 0 as well. Just keep doing that. X, y goes to 0, 0. Now we just have x goes to 0 when x equal to y. So just let x equal to y, so we have 3x. Y is also x. So 3x cubed, x squared, x to the fourth. So what this really is equal to. By the way, since all of them have x, even x squared is a common factor, we can simplify that. Simplify everything by x squared. We have 1 plus x squared and then 3x, right? We simplify x squared from all of them. Now, and now if we put in 0, we have 3 times 0, 1 plus 0 squared. So this is equal to 0. Well, that doesn't help. But that also 0. That doesn't say anything. If we go 2 paths, go to the same point. Well, that's great. But this is two-dimensional case. We have to prove that it go to, from every path, it have to go to the same number. So that direction doesn't work. But if we look at the graph one more time, it says that if it is in the parabola path, maybe the limit is different, right? Because it does have the parabola path here. Yeah, but you say, what's that limit? Does it look like equal to 0, right? Right. So now if actually we turn this a little bit out of the box, did you see it is also a parabola here, right? So this is the x-axis, the y-axis, so this is x equal to y. So along this path, it might be different. Let me turn this again. See, if we go along this path above, the limit will be different. So what we actually choose is along the path x equal to y squared. Y equal to x squared, if we do that, sorry, wrong one. If we do that, y equal to x squared, the limit is still 0 here, right? If we go along this path, y equal to x squared, x equal to, if we go along this path, the limit is still 0. But I think I have earlier when we turn this, and then very clear that this is x-axis, and we have x equal to y squared. So that look very nice there. So along x equal to y. Now the reason we can do this because the point it goes to 0, 0. If it does not go to 0, 0, cannot do that. Because if x equal to y squared, when x go to 0, y goes to 0 as well. Just say y go to 0. X equal to y squared. Right, now take the limit. As x, y go to 0, 0, the function 3x y squared of x squared plus y to the fourth. Now, I'm going to let x equal to y squared, and then I just need y go to 0. So I will have 3, x is y squared, and then we have y squared, x squared, y squared, square y to the fourth. So do that, I have limit y go to 0, 3y to the fourth, y to the fourth, y to the fourth, 2y to the fourth, cancel out, that is 3/2. So does that look like 3/2? Let me rotate this. Yeah, so that value says, yeah, it didn't have say the z values, but that look like that it should be 3/2 there. Of course, if we take it to negative y squared, then we should have negative 3/2 still. Now what we have here is this path is equal to 3/2. In another path, it is equal to 0. So different limit, different values from different paths. This limit did not exist. Right. So, and you say, what happened if we don't have the graph? Well, it will be more difficult, obviously. But the way we look at this, we see that we have x and y square, x square and y fourth. Look like there's the relation there. If we let the power of y is double the power of x on the top and at the bottom. So that's why we said the power of y is double the power of x. That's what the path we should choose. Earlier we have here the power of x and y are the same. So we choose y equal to x will work, or y equal to negative x also works. So if we have the power are the same, we're going to choose the same, y equal to x or x equal to y, or x equal to negative y. And if the power is different, then we choose the power accordingly. Y square, the power of y is double of x, so we're going to choose that. Now the theorem, this is just like the calculus of one variable. If it is continuous, the computation will be also continuous, so this is no big deal here. Next, determine which point the function are continuous. So the function is continuous. In this case, we should say there's the theorem in calculus 1. It says that the assumption function, if it is defined, it will be continuous. So we don't even need to find the limit here. Just need to show that the function is defined. And in that case, if it is defined, the function is continuous. Most of the function will be that way, except for the piecewise function. Absolute values also piecewise function doesn't work. But for all the function, I'm going to name now: polynomial, square root, rational function, trigonometry, log, exponential, pretty much all the function except for the piecewise function. For those functions, if it is defined, it will be continuous, right? So we just need to, this is the function in that class. So if this is defined, it will be continuous. And when we have ln, so let's graph ln and see what happens. Y equal to ln of x. Come on. Right. Because the graph only like this. So the function is undefined when x is negative or 0. So when we have the log, whatever we put there must be positive. Otherwise, it is undefined. And if it's undefined, it cannot be continuous, obviously. So we need is x squared plus y squared plus 4 greater than 0. Because we can move the 4 to the other side. Becomes negative 4. And this one obvious. Because x squared plus y squared, x squared, a square cannot be negative. So this one greater than equal to 0. Anything greater than equal to 0, obviously greater than negative 4. So this one, the limit is all real numbers. For x, all real numbers. For y, so in this case, they are continuous everywhere. And we have x and y, meaning anywhere in R2. Two variables. Yeah. So we just say it is continuous. On R2. Simple enough. Next we have this one, exponential function. Let's graph exponential function. I just say clear first, so it's much better. Right. So we have the graph. Well, I don't know why the it'll go extremely slow. But exponential function look like this. So which means it is defined for every values. But the only problem here is x divided by y. When we have divided by something, y cannot equal to 0. So because we divide by 0 is undefined, so we say the function is continuous everywhere except the x-axis, meaning except when y equal to 0. So that is where it is continuous whenever y is not equal to 0, because we cannot divide by 0. That's all. I really don't know what happened to the calculator, but it looked like frozen. Yeah, so that's bad. Now, the same thing for 3 variable. Approaching to a point in 3 dimensions is even more, I should say, still infinitely path from 3 dimensions to go from one point to another. So in that case, limit is difficult. But the first rule in limit is just put in the numbers and see what happens. So put 2 in for x, pi over 2 in for y, and 0 in for z. If that is equal to something, then we just say equal to sine pi over 2, sine 90 degrees, 1 over 4. So this is 1. So since this is a nice number, we're going to make it equal to. And I'm not going to even graph this because we can't. Remember, 3-dimensional space for x, y, and z, and we have 3 independent variables. There will be one more dependent variable. Put them together, that's 4 dimensions. We cannot graph it, so too bad. But we put in the numbers, it is defined, so that will be the limit. Right. Next, find the point at which this one is continuous. Right, and remember, I said I list all those functions before. Polynomial, square root, a rational function, trigonometry, log, exponential. Those functions are continuous whenever they are defined. So we just need to make sure that this function is defined, then it will be continuous. We don't have to worry about the limit. Right. So this is square root, and once again, if we have the square root, whatever we put in square root cannot be negative, otherwise we have imaginary. So we just have x squared plus y squared plus z squared minus 1 greater than equal to 0. Move the 1 over. Have x squared plus y squared plus z squared greater than equal to 1. So what is that? What we have is, if we have x squared plus y squared equal to 1, so we have to add another dimension to it. Yeah, so it is a sphere. So we have x squared plus y squared plus z squared equal to 1 is the unit sphere. Unlike the unit circle, but this is a sphere in space. So if it is more than that, meaning it will be outside of the sphere and including the boundary. So we said find a point at which they are continuous. We say it is continuous. Is continuous if the point xyz is on or outside. If it's more, I mean on the outside of the unit sphere. So that's what we have. So, yeah. So in terms of continuous and limit, there's something similar to it. I said if it is defined, it will be continuous for some certain function, like that. And those functions, once again, polynomial, square root, rational function like the quotient, trigonometric function, exponential, log, pretty much a lot of different functions. What doesn't work is the piecewise function. If we have a piecewise function, check the limit, check the values of the function, make sure they are equal. So certainly this thing will require for a piecewise function. Right. So, and last point I try to emphasize is that when we talk about the limit of function of two variables, consider it go from different paths. Unless we can evaluate directly like this, where we're trying to find the values, or we can simplify, then we find the limit. If it doesn't look like it can simplify to anything nice, and we have indeterminate, try to approach it from different paths. More likely the limit does not exist. Let me say that again. If look like it is equal to something, or look like there's something to simplify, then we can find the limit. If we cannot simplify, just try to approaching the limit from different paths. The limit might not exist in that case. Right. With that, I will stop this section here. And as always, thank you for watching.